When you look up at the stars, you can immediately determine their apparent brightness, at least comparatively, determine how bright they appear relative to one another. If you have some fancy instrumentation, you can take that light, put it through a spectrometer, and take a look at its absorption spectra. Use that as a fingerprint to identify its temperature, give it a spectral class, as we talked about in the last video, and precisely measure its temperature. So you can take the temperature of a star. But what else can we learn about the stars by dissecting the light that comes from it? Now in the picture here, there are two stars. One's called a white dwarf. In parentheses there, it's telling you a little bit about it. It's similar in mass to the sun, but it's the size of the Earth. So it's a very small star, but it's very massive. It's as massive as the sun. And then below it is a blue giant, which is, as it says, a giant star. It's a very, very big star. Yet both of these can have the same spectral class, meaning they can be the same temperature. A white dwarf can have the same temperature as a blue giant. So I ended the video talking about this idea that the temperature doesn't tell you anything about the size. Well, this is that point. A white dwarf can have the same temperature as a blue giant, despite being dramatically different sizes. But that doesn't mean their spectra are identical. So here's the spectrum of a white dwarf, and here's the spectrum of a blue giant. And you'll see that the lines match up, right? It has lines in the same place, and that's what determines its spectral class. But the lines don't look the same. Here they're wider and fuzzier. So there is a way to distinguish between a white dwarf and a blue giant, also by looking at the spectra. Now the next question would be, well, why are they different? They're the same temperature, so the lines go in the same place. But because the white dwarf is so much more compact, its surface gravity is so much stronger, the gravity in its atmosphere is so much stronger, that there's a much, much higher pressure. That added pressure has an effect on the absorption lines. It makes them wider and not as sharp as the lines of a much bigger star, where the surface gravity is much lower. And so here's one way we can distinguish the size of a star from its spectrum. The temperature alone doesn't tell us how big the star is, but looking at the spectral lines, we can gauge the size of the star by the width and the blurriness of the spectral lines, because that's telling us about the pressure in the atmosphere where the absorption happened. The next effect to the spectral lines is that they can be slightly shifted in one direction. Now, this relies on having a very precise calibration of where the line should be. And if you have the same pattern, but they're not quite lining up with your calibration, then what that's telling you is that the star is moving. This is the Doppler effect, right? The Doppler effect can shift the wavelength of light. Well, it's going to shift every spectral line. And if the lines are moved towards the red end of the spectrum, we call that a redshift. So here's the stationary star. Here is one that's redshifted. And what that tells us is the star is moving away from us. On the other hand, if the lines are moved towards the blue end of the spectrum or the purple end of the spectrum, then we have a blue shift, and that star must be moving towards us. So by the alignment of the spectral lines and identifying any shift, we can determine a star's radial motion, either towards us or away from us. That's what I mean. Along the radius between us and the star is radial motion. And radial motion can be a blue shift moving towards us or a red shift moving away from us. Now, a more subtle example of the Doppler effect is when the star is rotating. Now, it's not the whole star moving towards or away from us. That could still be happening. But within that, the light from each side of a star can be Doppler shifted. if the star is rotating. So in the picture we have one star that's not rotating, and so the light from each part of the star is the same, and the spectral line will be in a very sharp line. But if the star is rotating, the light from the side moving towards us gets blue shifted. The light from the side moving away from us gets slightly red shifted, and that makes the line a little bit wider. It broadens the line. And then in a plot of how much luminosity it has, you'll see a much sharper dip here where it's a little more spread out here. So it won't be quite as dark in the center as this one will be. And so we now have a few different ways to further dissect the spectrum. We can look for like width and fuzziness of the lines. It might tell us something about the pressure, but also the width might tell us something about the rotation, and those are effects that astronomers will have to parse out. Is it wider because it's a white dwarf, or is it wider because the star is rotating rapidly? But either way, that information is going to go into the spectrum. How the star is moving and the size of the star will affect its spectrum. Now this next example doesn't have to do with the spectrum of the star. It's the other way that a star can be moving. So when it's moving towards us or away from us in that radial direction, we can see the effect of that in the spectrum because of the Doppler shift. But if it's moving transverse to us, that doesn't show up in the spectrum. And by transverse, I mean perpendicular to the radius between us and the star. So here's the sun, here's some distant star. Transverse velocity would be like this way. So we can't see the effects of transverse velocity in the spectrum. So how can we see it? Well, we can see it by looking at changes in the position of the star relative to the stars that are around it. Now we call this, it's a little less obvious of a name here, it's called proper motion. So the star can have two types of motion: radial motion, which is towards us or away from us, and proper motion, which is side to side. So the proper motion of a star is how it's moving in our sky relative to the stars around it. So it's side to side motion. We'll look at some examples of that. The most prominent example of proper motion is a star called Barnard's star. It's the star that has the largest amount of proper motion. And this sequence of images shows how it moved from one decade to the next. So 85, 95, 2005. First, kind of think about the stars that are around it. You've got this V shape here, V shape here, V shape here. So from 1985 to 2005, you see the same pattern, right? That the pattern of stars is not changing, which tells you that these stars do not have much proper motion, right? They're not moving side to side relative to one another. And the same as if you look at the stars in the bottom, you'd see like this star, you kind of make a W here, right? Well, you can still make that W here, you can still make that W here. The one star that's moving is this one. It goes from here to here to here over a period of 20 years. That's proper motion. So proper motion is motion of a star relative to the stars around it, which means it's moving side to side. So that's not coming towards us or away from us, or at least that's not what we're detecting here. We're detecting it moving side to side in space, transverse to our direction to it. Now, most stars will not have a perceptible proper motion, which is why when you look up at the constellations from year to year, they look the same. The Big Dipper looked the same to your grandparents as it does to you now. Your great-grandparents, great-great-grandparents. The Big Dipper has not changed its appearance. But that's not true for every star. Some stars are moving on a time scale that we can actually appreciate. Now, if you go to a large enough time scale, all of the stars will have some proper motion because everything in our galaxy is moving, and it's moving relative to all of the things around it. They're not moving together. The constellations are not a group of stars moving in concert. They're all different distances from us moving in random directions. So 50,000 years ago, the Big Dipper would have looked like this and maybe would have still been recognized as like a ladle, but it certainly does not have the same shape as it does now. This star here, for example, has proper motion in this direction, so it's come in. This star also has motion in that general direction. It's going this way. This star is coming back. And so what it looks like today is this. If we fast forward, these stars all have this same proper motion. They're continuously moving through space. 50,000 years from now, this handle here is going to bend down, and the front of the ladle is going to tip forward, and this is going to have a new shape, maybe looking more like a S pattern, like a snake. And so the people around 50,000 years from now might have an entirely different name for this constellation than we do today. And this would be true for any constellation. All stars will have proper motion. It's just that it's so small and the time scale is so long over which appreciable change happens that we can consider them fixed. And so earlier in the semester, we were calling them the fixed stars. Here we're seeing that they're not actually fixed, but with the exception of a couple stars like Barnard's star from the previous slide, they are not going to move much over our lifetimes. Okay, so let's take a quick summary of the things that we can determine by analyzing the light from a star. Apparent brightness, you can just look up and see and record it on the magnitude scale where it is. Luminosity. Now, luminosity and distance I should talk about together. You need some other piece of information. So if there's a way to determine luminosity, you can figure out distance. If there's a way to determine distance, you can figure out luminosity. But we'll leave that for now. Provided we get a little bit more information, we can also determine luminosity and distance. Temperature, you just need the spectrum. You get the spectrum of the star, look at the absorption lines, say it's a type K. Well, type Ks have very specific temperature. Now we know the temperature of the star. Also the chemical composition. Remember, we didn't talk about this explicitly yet, but those spectral lines are identifying atoms and molecules. So also from that we can get chemical composition. What lines are there tells us what chemicals are there. You know, is there helium, is there nitrogen, are there metals present? All of those things are available from the spectrum of the star. Its size will be reflected in the spectrum because smaller stars will have higher surface pressure, surface gravity. Extremely small stars like white dwarfs will have extremely high surface pressure. That's going to cause a blurring in the spectral lines. On the other hand, very, very big stars where they're spread out very far and the surface gravity is not that high will have very sharp spectral lines. Radial motion we get from the Doppler effect on the spectral lines. Rotation we can also get from the Doppler shift because it causes the lines to broaden a little bit. And then proper motion, we can look up at the stars and see how they're moving side to side, record the positions of the stars very precisely, and then determine how fast they're moving in space. Well, as long as we know the distance, that proper motion will help us figure out their exact speed in space. And that allows us to begin mapping out the entire galaxy. So we're building quite a list of things that we can figure out about the stars just by collecting the light. Always keep in mind that that's our only resource as astronomers is the light that the stars are putting out. That light energy that we can collect here and analyze is what we use to determine everything that we know about the stars.